I have studied the agents chapter of this famous book by Chip Huyen called AI Engineering, along with dozens of other resources that I will summarize for you. This chapter is more focused on RAG and realistic ways of agents accessing tools that you don't want to miss out. So here's the roadmap. First, I will show you the exact moment when AI stops being a fancy autocomplete and becomes something that can actually think. Then we will go through why and how AI agents pick up digital tools, making them go from helpless to really useful assistants. This concept is closely linked with RAG, or Retrieval Augmented Generation, which I will discuss shortly. Next, the planning brain, the fascinating process of how AI learns to think ahead. Then the dark turn, when agents go rogue. I will show you why and where AI agents go completely off the rails, and the simple tricks that could prevent disaster. Finally, the world that's coming. By the end, you will understand why everything, your job, your creativity, even maybe your relationships, is about to change in ways most people can't even imagine yet. Let's start with the basics and a definition that has aged well. The term agent has been used in many different engineering contexts, including a software agent, intelligent agent, user agent, conversational agent, and reinforcement learning agent. So, what exactly is an agent? Going back to our Russell and Norvig AI book, an agent is anything that can perceive its environment and act upon that environment. So, here's the difference. Think about ChatGPT. You type something, it responds. One input, one output. That's not really perceiving and acting on an environment. That's just pattern matching on steroids. A true AI agent is constantly sensing what's happening around it, making decisions, taking actions, seeing the results, and adjusting its approach, like a really smart assistant who just doesn't answer questions but actually gets things done. The environment defines everything. If your agent is built to play chess, the chessboard is its universe. If it's designed to help with customer service, your entire business ecosystem becomes its playground. And here's where it gets uneasy. The more complex the environment, the more powerful the agent needs to be. Remember SWE agent? This coding agent treats your entire computer as its environment. It can navigate through file systems, search for specific code, view files, and edit them. So the main difference is that agents have access to tools to perform tasks. Let's see this in action with this interesting example from the AI engineering book. This is a simple agent with 3 actions: response generation, SQL query generation, and SQL query execution. Given the query, project the sales revenue for Fruity Fedora over the next 3 months, the agent might perform the following sequence of actions. 1. Reason about how to accomplish this task. It might decide that to predict future sales, it first needs the sales numbers from the last 5 years. An agent's reasoning can be shown as intermediate responses. 2. Invoke SQL query generation to generate the query to get sales numbers from the last 5 years. 3. Invoke SQL query execution to execute this query. 4. Reason about the tool outputs, meaning the outputs from the SQL query execution, and how they help with sales prediction. It might decide that these numbers are insufficient to make a reliable prediction, perhaps because of missing values. It then decides that it also needs information about past marketing campaigns. 5. Again invoke SQL query generation to generate the queries for past marketing campaigns. 6. Invoke SQL query execution. 7. Reason that this new information is sufficient to help predict future sales. It then generates a projection. And 8. Reason that the task has been successfully completed. Compared to non-agent use cases, agents typically require more powerful models for 2 reasons: compound mistakes and higher stakes. Compound mistakes is because an agent often needs to perform multiple steps to accomplish a task, and the overall accuracy decreases as the number of steps increases. For example, if the model's accuracy is 95% per step, over 10 steps the accuracy will drop to 60%, and over 100 steps the accuracy will be only 0.6%. And higher stakes is because with access to tools, agents are capable of performing more impactful tasks, but any failure could have more severe consequences. So essentially, given an environment, the success of an agent in an environment depends on the tool it has access to and the strengths of its AI planner. Tools help an agent to both perceive the environment and act upon it. So actions that allow an agent to perceive the environment are read-only actions, whereas actions that allow an agent to act upon the environment are write actions. More tools give an agent more capabilities, but here's the catch. The more tools there are, the more challenging it is to understand and use them well. So it's necessary to find the right set of tools through experimentation. Let me break down the 3 categories of tools and how they can and cannot be used. The first sets of tools are knowledge augmentation tools. These are like giving the agent a photographic memory of everything. Text retrievers, image analyzers, SQL executors, basically anything that helps the agent access information it wasn't trained on. This is where the RAG part that I talked about comes into play to help augment the knowledge of your agent. Think about it this way. ChatGPT's training data has a cutoff date, but an agent with web browsing, it knows what happened this morning. Stock prices, weather, breaking news, flight status, everything is current. This book uses web browsing as an umbrella term to cover all tools that access the internet, including web browsers and APIs such as search APIs, news APIs, GitHub APIs, or social media APIs. So augmenting the agent's knowledge is definitely the way to reduce the model's hallucinations. But the dark side is that it can also open up your agent to the cesspools of the internet. You know, all the rubbish materials. Remember we used to say in data, rubbish in, rubbish out? Now, the second category of tools are capability extension tools to give your model a performance boost. This is where things get really interesting. We are essentially patching the inherent weaknesses of AI models. Remember how LLMs are terrible at math? Give them a calculator tool and that problem disappears overnight. Instead of trying to train the model to be good at arithmetic, it's a lot more resource efficient to just give the model access to a tool such as calendar, time zone converter, or unit converter. But it goes deeper. These tools can essentially convert one model to a multimodal one without being trained on multiple modalities. For example, a model that can generate only text can leverage a text-to-image model as a tool only, allowing it to generate both text and images like a multimodal model without being so. The same goes for code interpreters that let text-only models execute programming code, or image generators let them create visuals, or even language translators break down communication barriers of text-only generative models. We are literally watching AI models evolve beyond their original limitations in real time. The downside of this, for example, by using code interpreters, is that automated code execution comes with the risk of code injection attacks, so it needs proper security measurements to keep users safe. Even so, this research shows tool use can significantly boost a model's performance compared to just prompting or even fine-tuning, where they showed a set of 13 tools can outperform GPT-4 alone on several benchmarks. Check out the link in the description box for all of this super interesting research. Now, the third category of tools this book discusses is write action tools, and here's where I get a little nervous, in the best way possible. These tools don't just read information, they change the world. SQL executors that can modify databases, email APIs that can send messages, banking APIs that can transfer money, social media tools that can post content. Suddenly, we are not just talking about AI that knows things, we are talking about AI that can do things, real things in the real world. Write actions enable a system to do more. They can enable you to automate the whole customer outreach workflow, reaching potential customers, finding their contacts, drafting emails, sending first emails, reading responses, following up, extracting orders, updating your databases with new orders, all of it. But it looks like we are still years away from that kind of trust in AI agents. For example, for bank transfers and other sensitive tasks, such as altering databases in real time. Here's what Chip Huyen had to say about this. Whenever I talk about autonomous AI agents to a group of people, there is often someone who brings up self-driving cars. What if someone hacks into the car to kidnap you? While the self-driving car example seems visceral because of its physicality, an AI system can cause harm without a presence in the physical world. It can manipulate the stock market, steal copyrights, violate privacy, reinforce biases, spread misinformation and propaganda, and more. These are all valid concerns, but this doesn't mean that AI systems should never be given the ability to act in the real world. Remember, the machines took us to space. The fourth and last category of tools that this book discusses is probably the most fascinating part of this book too: planning. But can AI actually plan? I mean, really plan? Yann LeCun, Meta's chief AI scientist, says absolutely not. He argues that autoregressive language models, the type that power GPT, fundamentally cannot plan because they can only generate forward, never backtrack. But then I saw agents in action. This is where many believe he's not right. Let me explain. The output of the planning process is a plan, which is a roadmap outlining the steps needed to accomplish a task. Effective planning typically requires the model to understand the task, consider different options to achieve this task, and choose the most promising one. Here's how AI planning actually works, and it's both simpler and more complex than you'd expect. When you give an agent a task like project the sales revenue for Fruity Fedora over the next 3 months, it doesn't just start randomly calling tools. It goes through a systematic process. 1. Task understanding. What exactly is the user trying to accomplish? 2. Plan generation. What sequence of actions will achieve this goal? 3. Plan validation. Does this plan actually make sense? 4. Execution. Take the actions outlined in the plan. And 5. Reflection. Did we accomplish the goal? What went wrong? So basically, planning at its core is a search problem. You search among different paths towards the goal, predict the outcome or reward of each path, and pick the path with the most promising outcome. Often you might determine that no path exists that can take you to the goal. This is what it means by saying search often requires backtracking. For example, imagine you're at a step where there are 2 possible actions, A and B. After taking action A, you enter a state that's not promising, so you need to backtrack to the previous state to take action B. But here's the catch in making AI agents backtrack, even autoregressive models. After executing a path with action A, if the model determines that this path doesn't make sense, it can revise the path using action B instead, effectively backtracking, just not the conventional way. The model can also always start over and choose another path. For example, the paper Reasoning with Language Model is Planning with World Model argues that an LLM, by containing so much information about the world, is capable of predicting the outcome of each action. This LLM can incorporate this outcome prediction to generate coherent plans. But then comes complex plans that are not just sequential planning with reasoning. To be able to understand this, we first need to run through the control flow. The control flow is the order in which actions can be executed. Here's an overview of 4 types of control flow: sequential, parallel, if statement, also called routing, and for loop. Sequential is executing task B after task A is complete, possibly because task B depends on task A. For example, first translate the natural language into a SQL query, then execute it. Parallel is executing tasks A and B at the same time. For example, given the query find me best-selling products under $100, an agent might simultaneously retrieve the top 100 best-selling products and for each of these products retrieve its price. If statement or routing is executing task B or task C depending on the output from the previous step. For example, the agent first checks NVIDIA's earnings report. Based on this report, it can then decide to sell or buy NVIDIA's stocks. And finally, for loop. In this control flow, the agent repeats executing task A until a specific condition is met. For example, it keeps on generating random numbers until a prime number. So you might ask, what makes this a complex plan if we already have these control flows in traditional software development? The answer is that now AI agents have to figure out which control flow type to choose based on understanding the natural language input you give to them. Not only the choice of the flow, but also generating a workable plan is more difficult now, let alone executing it. This is where reflection and error correction come into play, the most crucial component of an agentic system, which I fully explained in my previous videos, so check them out for a detailed overview. But essentially, reflection generates insights that reveal the errors to be corrected. Reflection can be done with the same agent with self-critic prompts. It can also be done with a separate component, such as a specialized scorer, which is a model that outputs a concrete score for each outcome. To do this type of complex planning, a group of researchers proposed the REACT method, which stands for Reasoning and Action in a Chain of Thought, where the agent spits out its thinking and reasoning process, then it takes action and analyzes its own action with reflection and continues to do so until it finds the results, as you can see in this example. As you can see, during this process, the agent needs to access tools, but here are the crucial points that most agentic tutorials do not teach. To help the agent decide which tools to use and how to use them, you need to consider these super important steps that get you to the top 1% of agentic system designers. First, compare how an agent performs with different sets of tools. Second, do an ablation study to see how much the agent's performance drops if a tool is removed from its inventory. If a tool can be removed without a performance drop, remove it. Third, look for tools that the agent frequently makes mistakes on. If a tool proves too hard for the agent to use, for example, extensive prompting and even fine-tuning can't get the model to learn to use it, change the tool. And finally, just as this research has done, plot the distribution of tool calls to see what tools are most used and what tools are least used. But even with all this, using tools by agents can fail for a number of reasons that you need to consider while making your AI agents. First is the invalid tool. For example, it generates a plan that contains a tool which isn't in the tool inventory. Or the case of valid tool but invalid parameters. For example, when the agent calls multiple parameters when only one is needed, or vice versa. And finally, valid tool, incorrect parameter values. This is when both the tool and parameter type are valid, but it generates a wrong value for the parameter. For example, to convert pounds to kilogram, it incorrectly uses the value 100 for pounds when it should be 120. As you have already noticed, designing an agentic workflow, even for simple tasks, requires understanding the main design elements of an agentic system that I explained in detail in this video.